Oh, goodness. The presentation just stopped. Apparently, I'm having serious problems today. Okay. Give my little technical issue. I'll give the tardy people a break here. Austin. Chad still not here. Toussaint. Okay. Let's see, two things people have asked questions about. Number one is, will there be scaling for this exam? And the answer to that is no. This exam had a much higher average score, much more reasonable. Second thing, just in case I forget, for Friday, do concept coach through 30.5. Today was through 30.1. Okay, so we are technically in the section on quantum mechanics, and today is actually the only lecture on quantum mechanics. It's very small in this book. Quantum mechanics starts with the wave-particle duality. So it was Einstein who really was the true believer that light had a particle nature, brought it back. And so we start with Einstein having light having a particle nature, but Einstein did not say that light does not have a wave nature. He just said it also has a particle nature. We had a question about that, a clicker question, because it's a weird thing. Usually we say a scientific experiment disproves something. And so, for instance, Thomas Young had disproven that light was a particle. That had been the belief based on Newton's work. But now Einstein did an experiment. Instead of saying he disproved that light was a wave, he recognized, okay, we have two experiments that give competing, contradictory answers to the true nature of light. And so Einstein said, we really need to fold it together and say the experimental evidence is that light is both a wave and a particle. And if you have a wave, then if you have that wave go through the double slit, some of the wave goes through one slit, some of the wave goes through the other slit, and then the wave that went through one slit interacts with the wave that went through the other slit, and we get constructive and destructive interference, giving us a diffraction pattern. So that's what we've learned about a wave-particle duality so far. We're going to move that forward, but before we do, just some quotes to make sure people don't feel dumb. These are some of the great minds in physics. Niels Bohr. Anyone who has not been shocked by quantum mechanics has not understood it. Right? This stuff is not obvious or simple. And if you think it's obvious and simple, that's just a sign that you don't understand what it's about. Richard Feynman, considered the greatest mind of our time, at least the greatest scientific mind of our time, he died when I was in college, said, I'm going to tell you what nature behaves like. If you simply admit that maybe she does behave like this, you'll find her a delightful, entrancing thing. That is kind of the opposite of the way I tell you to treat any class, not just my class, but any class. In no class should you sit there at the fount of knowledge and just slurp it up and say, teacher said it, so it's true. Right? That's not learning at all. That's being indoctrinated or being brainwashed. And yet here Richard Feynman saying, I'm going to tell you how nature behaves. And if you admit that maybe it does this, you're going to find it really intriguing. So this is an area where our practical experience really doesn't have much value. It's a lot more complicated. It takes a lot more mathematics and work to really understand the basis of quantum mechanics. And that's why this section is brief, because it's pretty complicated. We'll have a little bit more in the Tuesday class, but not much. And we start with an understanding of probability. How many people have heard the famous quote about Einstein talking about God playing dice with the universe? Wow. Usually more people have heard it. Well, the quote goes something like, I don't believe that God plays dice with the universe. What was Einstein talking about? Well, first of all, Einstein, depending on the day of the week, I suppose, and what he was addressing, was either agnostic or atheist. He wasn't the person who would be out there teaching to believe in God that I believe in. So he wasn't talking about the God I believe in when he said God. He does have other quotes like, science without God is meaningless, and God without science is, I don't know, ignorant or something like that. Which is more in line with talking about the God I believe. But in this case, when he says, I don't believe God plays dice with the universe, he was saying, I don't believe this quantum physics crud. That's what he was really saying. Because quantum physics is probabilistic. That is, quantum physics tells us, well, there's a 70% chance of this happening, and a 20% chance of this happening, and a 10% chance of that happening. It doesn't tell us what's going to happen. It just tells us what the probabilities are. And we make a measurement, and it's like going gambling. You don't know what it's going to be, but you can determine what the odds are. If I go to Las Vegas and I play roulette, I can calculate the odds of how much money I'm going to lose per hour. But I can't tell you exactly how much money I'm going to lose per hour. I might win, because it's all based on probabilities. But you do know if you go gambling, the odds are always stacked against you, right? Probabilities are you're going to lose. Unless you're playing something like a game of skill. Poker's a game of skill because you're seeing who can lie better. So, Einstein was making a statement that he did not believe that God, which in this case was Mother Nature, if you will, he was referring to nature as God. That nature is not simply a gambling game. It's not probabilistic. Basically, Einstein believed that if you have enough information, you can always predict what's going to happen. We call that determinism. And up to this point in physics class, everything we've done was deterministic. Now, you might argue with me. You're free to do that. You might say, well, you talked about statistics, and I told you that thermodynamics is statistical physics. We're calculating probabilities there. But the difference is, we're calculating probabilities because we have no way of taking all of the data, collecting it, and then analyzing it to predict what's going to happen. But thermodynamics says that if we knew the positions and the momenta of all the particles, we could exactly predict what's going to happen to each particle. But quantum mechanics really is saying that nature is not deterministic, that you just can't determine what's going to happen with an experiment. It could go one way, it could go another. We can determine the odds of it, but that's all we can determine until we make the measurement. So, probability. All of that was for the probability. When we talked about light going through the double slit experiment, we could talk about light as a wave, or other times we talk about light as a particle. And so I want to look at how we deal with probability with light, something we already understand, or I believe we understand. So the intensity of light, that's what we generally perceive. Light here because it's bright. No light there because it's dark. And the intensity of the light is the energy per time per area. But if we are going to use the wave nature of light, then we have a wave function, the electric field, that describe the light wave. The light wave, obviously the wave function describes the light wave. And the intensity was proportional to the electric field amplitude squared. So where we're going to have more light is where we're going to have a higher electric field amplitude squared. Where we have less, small electric field amplitude squared. Simple enough concept? Well, now, let's go to the particle nature. The particle nature of light says that the intensity is going to be the number of photons per time per area that hit a spot, multiplied by the energy of those photons. Well, if we take that, we can recast it as the intensity is proportional to the probability of finding a photon at a certain point in a given time in an area. Well, at a given time. So what we have here is the outcome is the intensity is proportional to the probability squared, but the intensity was also proportional to the electric field amplitude squared. And that is really what leads us into quantum physics. Right there, we have a wave function, the electric field, that tells us what the probability is going to be of the particle being there. If I just combine those two together, the electric field squared is the probability squared of a particle being in some location at some time. Yes?
Wait, sorry, what's the probability squared?
Why is the probability, excuse me, you're right, it's not squared. That is my mistake. I'm glad you corrected me, or we would have gone forward and then I would have really scratched my head. Probability is proportional to the electric field squared. Yes. Whew. Thank you, Tori, for helping me avert a big problem. Now, going from there, I believe this is going to be, this is the summary. The probability of finding a photon in some region of space is proportional to the square of the wave function in that region. What is the wave function for light waves? The electric field. Thank you. Okay, now I think we go to question to make sure we understood that first aspect of quantum physics. What aspect of the electric field, or wave function, gives the probability of finding a photon at a given location? Answers are slowly converging on the right answer. I'm assuming that means people are talking to each other, which, frankly, I'm okay with that, as long as you're learning. One person's explaining to you what they got so you can get what I've been talking about. Sally and Chad. Okay, so we had only two answers. Only one person said the amplitude. Everyone else said the square of the amplitude. That's good, because that was the key here. The probability was proportional to the square of the amplitude of the wave function, which for light was the electric field. Now we have Louis de Broglie. In his PhD thesis, which was like 20-some pages, very different from mine or anyone else's today, Louis de Broglie suggested that maybe it's not just light that has a wave-particle nature. I always like to say, he's like, what about me? You know, if light can have a dual nature, why can't I? And so de Broglie hypothesized that maybe everything has a wave nature and everything has a particle nature. So we tend to think of electrons as particles, protons as particles. You and me, baseballs, particles. But Louis de Broglie said, what if we could treat all of these things like waves? And he said, well, if we could, then we should be able to use light, our first thing that has a dual nature that we're now convinced of, as a guide. So for light, we have a relationship that the wavelength of light relates the momentum by Planck's constant. That is, the wavelength was equal to Planck's constant divided by the momentum. So de Broglie said, let's take something else, like say an electron. Almost everything we do here is with electrons. And say the wavelength for the electron is equal to Planck's constant divided by the momentum of the electron. Now notice the time, this is in 1923. We have Stern and Gerlach, who did some experiments from 1923 to 1927, exploring this idea. And so what they were doing is they were shooting electrons at a crystal. Now we've learned about diffraction. A crystal is a material that has a repeating pattern of where the atoms are. And because of that repeating pattern, it acts for light waves like a diffraction gradient, like a three-dimensional diffraction gradient. And so Bragg did work to explain how diffraction should occur from a crystal. So in Davisson and Germer, I said Stern and Gerlach, didn't I? I said Davisson and Germer, or Germer. Stern and Gerlach were studying the magnetic moment of silver atoms. Different thing. So the Davisson-Germer experiment, they found that when they had a beam of electrons striking a crystalline surface, and I don't remember what the crystal was, that they had a scattering angle of 50 degrees. That is 50 degrees between the incident ray and the scattered ray, where they had the most electrons. If you apply Bragg scattering equations, they found that for the material they were studying, this 50 degrees was the angle predicted by Bragg scattering. Like I said, we haven't studied Bragg scattering, we've studied just double slit and diffraction gratings. But it matched if you used the wavelength equal to the de Broglie wavelength. So what they have now is an experiment that would test if electrons really behave like waves, and the experiment confirms yes, the electrons diffract like light waves would if they had the wavelength given by the de Broglie wavelength. Now, does that prove de Broglie right? Okay. If I say, does that prove, you always say, no. No, it doesn't prove it right, but it gives you some reason now to maybe think, maybe de Broglie's right. Maybe particles can have a wave nature. So maybe electrons can be treated like waves instead of particles. Further experiments, here's some work by George Paget-Thomson looking at crystals that have been crushed. And so you just have a powder. And then you can take these powders and you shine an X-ray on them, and you see diffraction patterns from the... They're all different orientations, so that's why it's circularly symmetric. But you see the diffraction patterns, and if you did that with electrons, you got nice, clean diffraction patterns as well. So another example showing, hey, the electrons diffract just like light waves would. The description here. So what we end up with is, yeah, we believe that electrons must be showing a wave nature. Now this is getting, it's getting more real because most of us think of electrons as little balls and it seems real, even though who's seen an electron? None of us, right? But we've talked about them enough that they feel like particles we know. Well, now we're saying they're waves. And what does physics really say? Electrons are both. You can treat it as a particle, you can calculate, the approximate size of an electron, or you can treat it as a wave. Now, we had the Young's double slit experiment. So if electrons are waves, we should be able to use Young's double slit experiment with electrons. So here's a figure from our textbook showing what happens. If you have just a few electrons, it's kind of hard to see a pattern. But if you have more and more electrons, you see a clear pattern. You see a diffraction pattern. Now let's back up a step. We have two slits, and we shoot electrons at them. If the electrons are particles, we have two slits. What can you tell me about the electron going through the slits? If it goes through, what did it have to do? Okay, let's look at this room and you people being the electrons. We have two doors. If you're in here, what can I say about you with respect to going through doors? You went through one or the other. We never say you went through both doors, right? We just wouldn't say that. So if we're treating electrons as particles, we say the electron went through that door or it went through that door. But in that case, if we're treating as particles, what should we have for the pattern of the electrons just traveling in straight lines? We should have a pattern that basically replicates the two doors. On the other hand, if you're a wave, like a light wave, and we have the two doors, we say, well, light came through both doors and then interfered. So now we talk about the electron, having a wave nature. We say the electron went through both slits. One particle can't go through both slits, but one wave can go through both slits. So the electron went through both slits, and then the wave that went through one slit interfered with the wave that went through the other slit to give us our diffraction pattern. For most people, that's a really uncomfortable thing to think about. To think about the electron not being a particle, but being an object that can be going through two slits at the same time. But that's necessary to build this diffraction pattern. Now, what if we want to test it? If we make something that can measure if the electron went through slit A or if it went through slit B. If we put that device in to measure which slit the electron went through, it changes the pattern. And you have a pattern that looks like BBs going through the slits. Is that interesting, bizarre, weird? By measuring, you forced it to act one way. By not measuring, it went through both. And so you have different behavior if you measured which slit it went through, or if you didn't measure which slit and just looked at the pattern. This leads us to electron microscopes. In my research, I was looking at vaporizing materials with lasers, and to try to figure out what kind of damage I was doing to my materials, I wanted to see high-resolution images of the surfaces. And if you're using a traditional light microscope, your resolution is limited by the wavelength of the light. You can't see details essentially better than about the wavelength of the light you're using. So the shorter the wavelength, the better resolution you have. So for instance, in biology, you might have a microscope that uses blue light. How many people see a microscope that uses blue light? Okay, none. Well, the reason you have a microscope using blue light is because blue light is the shortest visible light. Using the shortest visible light, you're improving the resolution. You can see smaller details. Or some biology microscopes, you actually put your sample in oil. And you put your objective lens in oil. So it's oil between the sample and the objective. Why? What does it do to light when you go through something with a slower speed? It's slower, so what does that do to the light? It changes the wavelength. The frequency stays the same, but it shortens the wavelength. And by shortening the wavelength, by putting that oil in there, you shorten the wavelength and you get better resolution. Well, that's just generally not good enough for things. And so we need shorter wavelengths. What can we make? What kind of electromagnetic waves do we say that have shorter wavelengths than visible light? Ultraviolet, X-rays. So you could have, for instance, an X-ray microscope and you'd be able to get better resolution. Or an electron, since de Broglie says that the electron, a particle, has a wavelength that is equal to Planck's constant divided by the momentum of the electron, I can just adjust the momentum of the electron. I go through a bigger electric field or bigger voltage difference. It's going to have a bigger momentum. If I have a bigger momentum, then I'm going to have a smaller wavelength. And so simply by adjusting the energy, and that's the momentum, of my electron, I can adjust its wavelength and I can get very short wavelengths with my electrons. And so there are a number of microscopes that are based on electrons. And you tend to think that is, I'm shooting it with a shotgun of particles, electrons, but the way it's working is I'm shooting it with a bunch of waves with very short wavelength. And then we use, obviously for lenses you have to use something different than glass, but you can make lenses using electric field gradients, and you can focus the waves of the electrons. And so you can get very short wavelengths for the electrons, and thus very small detail can be resolved. So you can have something like a scanning electron microscope, usually called an SEM, or a transmission electron microscope called a TEM. I underlined the SEM because I have a lot of experience with an SEM. And those give you better resolution because you're using the wave nature of electrons to get a small wavelength and thus better resolution. Exciting, isn't it? It's an application. It's how this is useful. An application of the wave-particle duality applied to electrons. Now, we don't make scanning proton microscopes. Why not? Well, protons have a lot more mass. With a lot more mass going through the same, going through the same voltage difference, you'd have the same energy, but since energy is relativistically, hard, classically, kinetic energy is p squared over 2m. So if you have the same kinetic energy, but more mass, you have a smaller momentum, and you have a then smaller or bigger wavelength. So to get the short wavelengths with the proton would be harder. So we stick with the electrons. And you basically will burn a hole through your material. I burned holes through plenty of things with the electron beam. Okay, what is the key idea of Louis de Broglie's hypothesis? Okay. "11 people hit the nail on the head. Electrons have both a particle nature and a wave nature was his key part. Do electrons carry momentum? Yes. Particle nature would have said they carried momentum. Wave nature would have also said they carried momentum. Do electrons scatter? Yes. Now, particle nature can explain scattering. You have like billiard balls scatter. Probably all seen that. Wave nature also explains scattering in different ways. So scattering can occur for both. Photons can carry momentum. We learned about that when we were talking exclusively about waves. With particles, it's a lot easier to understand them carrying momentum. And then we have, photons can scatter. Well, yes, of course they can. Photons have both particle and wave nature. That was from Einstein primarily, and Planck. I, by the way, have 53 slides here. We're not going through all of them. I'm putting the extra slides on there so people who are more interested in quantum mechanics can look at them. Now we come to one of the really bizarre things about quantum mechanics, as far as most people are concerned, the Heisenberg uncertainty principle. Now, Werner Heisenberg, the next slide is about Werner Heisenberg, so I won't talk about him right now. But he formulated a principle that says the uncertainty in position multiplied by the uncertainty in momentum is always greater than or equal to 1/2 of Planck's constant divided by 2 pi. Now, that Planck's constant divided by 2 pi is so common in physics that it has its own name. It's like the Planck's reduced constant or something like that. Other people call them different things. Usually we call it h bar. So h bar is h divided by 2 pi. And that uncertainty is the product of the uncertainty in position times the uncertainty momentum. So to put that into perspective, I am up here and you could say, okay, Richard's position is, X number of meters from the wall and X number of meters from the screen. Right? You can identify my position. Then you have, what's the uncertainty on that? And depending on your measurement, you come up with an uncertainty. And then you would say, probably Richard's stationary. And so what would my momentum be if I'm stationary? 0. But this here says that if I multiply those two together, it has to be bigger than some minimum value. That is, I can't arbitrarily know exactly the position and exactly the momentum. The more accurately I know the position, so the smaller the uncertainty in delta x, the less accurately I know the momentum. The bigger the uncertainty, momentum. Now, the first question everybody wants to say is, well, is that simply a limitation of our measuring devices? And no, it is not. It is a limitation on nature. And so we're going to go through, remember the next slide's on Werner Heisenberg, and then after that, we'll go through some to understand how this uncertainty relation even comes about. So first, Werner Heisenberg. Werner Heisenberg, a brilliant physicist in the emergence of quantum mechanics, but he has one flaw as viewed by the Western world. Unlike Einstein and others who fled the German Empire in World War II, he stayed and he was in charge of the Germans' efforts to build the nuclear bomb. Now here in America we had Oppenheimer, who was in charge of our bomb. Oppenheimer, surprisingly to most people, was a socialist. As long as he was building a bomb for us, that was okay. People said, that's okay, you can be like Bernie. But after they built the first nuclear bomb, and by the way, Richard Feynman, who I quoted earlier, was the youngest person working on the Manhattan Project to build a nuclear bomb. After they built the nuclear bomb, which is a fission bomb, scientists realized real quickly, we could get a whole lot more bang for our buck if we made a fusion bomb instead of a fission bomb. And so the government asked Oppenheimer to come back and oversee creating a new fusion bomb. And Oppenheimer said, no, I'm done with making death machines. And then all said, you commie pinko. And he was, got the negative aspects of the Red Scare. So it's interesting to think about just the political aspects that went on with science back then. And when we talk about nuclear power, I'll talk more about that. But Werner Heisenberg was the German equivalent. He was the one working with the Germans to develop their nuclear bombs. How many people knew the Germans were working on nuclear bombs? Okay, a few people. That's the whole reason we worked on them. Because the Germans placed an embargo on information related to nuclear physics and on the export of certain nuclear materials. And American scientists said, whoa, there's huge energy that can be released. They're not sharing information anymore, and they're keeping the materials. They must be working on a bomb. And the whole Cold War mentality. If they have a big bomb and we don't, then the balance of power is huge. They have a big power advantage over us, and they're going to blow us up. We'll all be, speaking German. And so they wrote a letter. They had Einstein sign it because Einstein was such a major character in the scientific world, to the president saying, we believe the Germans are building a bomb. It's very possible. And we believe we're going to have to do something to keep up with them. And so that's what started the Manhattan Project, developing that first fission bomb and later the fusion bomb. Okay, so enough of that history. It's important to have some relevance about how science plays out in the real world, but at the same time, it's not for today's lecture. So, an explanation of how the Heisenberg uncertainty relation comes. And this is actually how Heisenberg's relation is calculated to show a mathematical proof. Because in math, you can't have proofs. When we talk about a photon, we're talking about a particle of light. And if I ask you, where is that particle of light, it's kind of hard to define. If you look at a wave for that particle of light is defined by a wave that we call a wave packet. You basically have a flat line, no electric field, all of a sudden, and then flat line. And where it's wiggling, somewhere in that region where the electric field is oscillating, that's where you have your wave packet, your photon. So in this picture here, I would say my photon is somewhere between my hands there. This picture here, right, you see different spreads. So I would say the uncertainty in position here is going to be something like that for the first picture. Uncertainty in position be something like that in the second picture. Very different uncertainties in position based on the shape of that packet. Now, what tells us the momentum of a particle? According to de Broglie, according to de Broglie, the momentum is h over wavelength. Now, these two pictures both have the same wavelength, so you have the same momentum, but, and here's something where a little extra calculus might help, those two packets are not just one wavelength. If it was one wavelength, it would look like the next slide's going to look. Here, let's take a quick peek. There's one wavelength. It goes on forever. That's one momentum, and where's the position of the particle? Anywhere. Right there you have an exact momentum because it's only one wavelength. No uncertainty in momentum. But you have an infinite uncertainty in position. In the case we're looking at right here, we have a finite uncertainty in its position, but in order to make that packet, you have to mix lots of different waves together. And so you have lots of different wavelengths that are required to make that packet. And so we can actually graph a Gaussian distribution of the wavelengths necessary to make that packet. And just like I had an uncertainty in position here, we then have an uncertainty in the wavelength, which translates into an uncertainty in the momentum. And the smaller the packet, so this one here is the smaller packet, the bigger the uncertainty in the wavelength, hence the bigger the uncertainty in the momentum. The bigger the packet, the smaller the uncertainty in the momentum, but the bigger the uncertainty in the position. And so using Gaussian wave packets, it can be proven mathematically that that gives you the smallest product of uncertainty of position with uncertainty of momentum. And in the case of Gaussian packets, you have the uncertainty in position multiplied by the uncertainty in momentum is equal to h bar over 2. So the Gaussian packets is the minimum case. Any other case is greater than that. So that's the fundamental, it's the fundamental aspect of the wave-particle duality that says if you measure position and momentum, you can't know them both at the same time. Now, is this practical for us to think about? Let's think about an automobile. I put my automobile in the garage. And so since it's in the garage, I close the door and I can say, well, I know it's in the garage, so I have an uncertainty in its position that's, this big for my garage. And using this, I can then calculate what my uncertainty in the momentum is. Well, Planck's constant, 6.626 times 10 to the minus 34 joules times seconds. If I have an uncertainty position that's 2 meters, and I take that, I say, okay, delta P then is greater than or equal to h bar over 2 delta x. And so I have 6.66 times 10 to the minus 34 divided by 2 times 2 meters. That's still on the ballpark. Actually, it's 1 when you have h bar. I made a mistake there. But it's still on the ballpark of like 10 to the minus 34 kilogram meters per second for the momentum. 10 to the minus 34 kilogram meters per second, to you and me, that's at rest for the car. So we would say, yeah, the car's at rest and it's in the garage. Hence, this doesn't really affect us. But let's suppose that Planck's constant, that h bar was something like 100. Or even better, let's say it's 10,000. If Planck's constant was 10,000 joules times seconds, and our car had an uncertainty in position of 2 meters, then its uncertainty in momentum would be 5,000 kilogram meters per second. Divide that by the mass of the car, and the car could be going, 100 meters per second or so. You don't know. And so if Planck's constant was a big number instead of a small number, it would really affect us. If we parked the car in the garage, we'd be afraid to step into the garage because the car could run over us. Because it could be traveling 100 meters per second in there. I don't know. So it becomes unimportant, that is, the uncertainty principle becomes unimportant for everyday sizes because Planck's constant is very small. For very tiny sizes, it becomes important because you're dealing with small dimensions and small masses. Already talked about that. Another example for the proof of Planck, or the uncertainty relation. This one actually gives you the equation, but I'm not going to work it out because I want to go through more. If we have a little slit and electrons go through, what's going to happen to the electrons on the screen out here? What's it going to look like? I get a diffraction pattern that's going to be tall in the center and come down and go like this. And so we have here's m equals 1, m equals minus 1, where a sine theta m is equal to m lambda for destructive interference. If we have electrons going through here, we can calculate the wavelength based on their energy, their momentum. And so we can go through and we can calculate what that angle is. And with that angle and its momentum, we could calculate, we would have px like this, and uncertainty and momentum in the y direction like this. So based on the angle theta 1, I could just say, well, tangent theta 1 is equal to uncertainty momentum in the y direction over momentum in the x direction. And so that gives me something about the uncertainty in the momentum, and then I can calculate the uncertainty in position is 1/2 of that slit width. And putting this equation, and this equation together, I can then calculate what the product of the uncertainty in momentum in the y direction is, and the uncertainty in position in the y direction. Like I said, I'm not going to do it. This next page is just what I had set up for doing it. But there's another example of a derivation. That derivation doesn't give you the exact minimum value because you weren't using the two Gaussian packets. But it illustrates when light goes through the slit, or when a wave goes through the slit, its position expands, so you have an uncertainty in its momentum perpendicular to that slit, and you also have an uncertainty in its position perpendicular to that slit as it went through. That's not the only uncertainty relation. We also have an uncertainty relation between energy and time. Now, in quantum mechanics, we go through how this is derived. It's not just all uncertainty relations are greater than or equal to 1/2 h bar. And it's not every pair of possible variables have an uncertainty relation. But it turns out that these are the same. And this is very, quote, practical in particle physics. I say in practical in particle physics because particle physics, most people would say, is relatively impractical. But in particle physics, you do things like you bash two things together. And the goal is when I bash those two things together, I'm going to make something with high energy. But that thing with high energy is then going to break apart. And you can measure things like the lifetime of your particle, and assuming that you are roughly on the boundary of the uncertainty principle, you can then say, the lifetime had an uncertainty of this amount, like it lasted this long, and some of them started decaying here, and some of them started decaying later, had an uncertainty in the lifetime that was this long, and so it must have had this much energy. And so this is actually used in particle physics all the time as a way to look at the time for a decay and then to calculate what the energy associated with that decay was. Yeah?
Does it give you the uncertainty of the amount of energy?
Yes, it gives you the uncertainty amount of energy, but they assume that the uncertainty is the energy. There's assumptions here, but they're reasonably founded. You don't know exactly what it is, but they're reasonably founded that the energy is approximately equal to the uncertainty. Okay. Now, quantum physics and its practicality. Next Tuesday in our calculus class, if you want to learn more about quantum physics, we will be doing the particle in the box problem. That is, we'll be doing a problem where we say, I have an electron, and this electron is constrained to be within this box. And if it's constrained to be within this box, then it turns out that it can only have certain energies. If it's not constrained, the electron can have any energy at all. But if it has to be in this box, it can only have certain energies. Now, how is that applicable to the Physics 152 class? Well, we are moving from this, chapter 30.1, where you're supposed to go through for Concept Coach today, with starting with atomic models. And the atomic models come to a quantum model. And in the quantum model, we say that the electrons are bound to the nucleus. They can't leave. And so they have a certain range they can be in, and because they have a constrained range, that means there are only certain energies the electrons can have. A free electron can have any energy. So if you have an unconfined particle, you can have any momentum, any energy. But as soon as you confine it, as soon as you constrain it, there are only specific energies that it can have, and only specific momenta that it can have. And so we will start with the Bohr model when we actually, on Friday, we'll start talking about the models and get to the Bohr model. And Bohr made a quantum condition where he simply said, let's suppose the electrons have only specific quantized angular momenta available. And you get the Bohr model, which immediately Bohr realized, well, this can't be right. And we move from there to the quantum model. Okay, so let's talk about the quantum mechanics. First, we started at the beginning of today's lecture talking about electric field. And I said that electric field serves as the wave function for light. And so quantum mechanics is moving. We have Louis de Broglie said, well, an electron should be able to be a wave or a particle. And so Erwin Schrödinger said, well, if an electron can be a wave, then I should be able to have a wave function for it, just like I have the electric field wave function for a photon. And his colleague said, oh, if you're so smart, what's that wave function? And so he worked on it for, I think it took him about 9 months. And he came back and he came up with a wave function. Or actually, he came up with a wave equation. Wave equation, wave function. The words start to get messed in my mind. One of them is an equation you use to find the other. The wave equation, the wave function. Yeah, he came up with the wave equation. The wave function is what we've been talking about, the electric field. The wave equation is the equation you use to find that function. And so he came up with this wave equation that is really just an energy balance equation. It's going all the way back to what we've done before about the total energy is the kinetic energy plus the potential energy. And so he makes this differential equation. It's a second order linear differential equation that allows you to find what your wave function is. And so psi, which is this Greek letter right here, is the symbol we use for that wave function. So you use the wave equation to find this wave function. And that wave function gives you all of the information about the particle. All of it. You just have to find a way to pull it out. But the first thing we talk about is this psi is the wave function for a photon. It was the electric field, so the psi is equivalent E, Q, U. I can't spell to save my life. It's equivalent to electric field. And we learned that if I took the electric field, I could find the probability of where my photon is from the electric field. How did I do that? I have to square it. And so if we take this psi, this wave function, and we square it, I know I'm on the wrong layer, and that's why I erased through. If we square this wave function, it will tell me the probability of my particle being in a certain location. So this wave function is also called the probability density. My brain is not. Probability density, because it turns out the probability is equal to the integral from A to B. The probability of being between positions A and B is the integral from A to B of psi star psi dx, or as we like to write that, the absolute value squared of psi dx. It's a little bit different because we have to integrate over a range, that is, add up all of the probabilities from this point to this point. Because the probability of being at exactly any point is 0. You have to look at the probability of being between 2 points to have a finite result. And so that wave function gives the probability density, which we can then use to find the probability of a particle being here. And that's where we will end today. That's where we'll end our quantum physics. We'll start talking about atoms on Friday.